Good morning all. Today we discuss the crystal physics. In this chapter, we have to discuss lattice point and space lattice, basis, crystal structure, unit cells, lattice parameters, primitive cells, crystal systems, and symmetry, the 23 symmetry elements in cubical system, rotation axis and inversion, Draw's space lattice, metallic crystal structure, structures of sodium chloride, diamond, zinc sulfide, hexagonal and closed pack structure, direction, planes, and Miller indices. To discuss the topics, our textbooks is Solid State Physics by S.O. Pillai. Then, what is solid state physics? Solid state physics, also known as condensed matter physics, it is the study of behavior of atoms when they are placed in close proximity to one another. In fact, condensed matter physics is much better name since many of the concepts relevant to the solids are also applied to liquids. Then the classification of matter. Matter is mainly classified into gases, liquids, and solids. Now, about gases, we know that gases have atoms or molecules that do not bond to one another in a range of pressure, temperature, and volume. These molecules haven't any particular order and move freely within a container. Then about liquids. Similar to gases, liquids haven't any atomic or molecular order and they assume the shape of the containers. Applying low levels of thermal energy can easily break the existing weak bonds. Then solids. Solids consist of atoms or molecules executing thermal motion about an equilibrium position fixed at a point in space. Solids can take the form of crystalline, polycrystalline, or amorphous materials. Solids have stronger bonds between molecules and atoms than liquids. Solids require more energy to break the bonds. Then the classification of solids. Solids mainly classified into different categories. Just look at the video.
Solid state. Classification of solids. Now, if you look at diamond and glass, we can see that both are solids. But if you look at them at microscopic level, we can see that there is a difference in arrangement of constituent particles. In diamond, the particles are arranged in an orderly fashion, whereas in glass, they are completely disorganized. Based on the order of arrangement of constituent particles, the solids are mainly classified into two types: crystalline solids and amorphous solids.
So mainly the solid is classified into crystalline and amorphous. But the crystalline also classified into single crystal and polycrystalline. So we can say that solid materials is classified into crystalline, polycrystalline and amorphous. And the crystalline is considered to be single crystal. Now the crystalline solid. From the played video, you must have got idea about crystalline solids.
Let us discuss about crystalline solid. In a crystalline solid, the constituent particles such as atoms or ions or molecules are regularly arranged in a definite pattern for a long range. Here, the arrangement is so regular that by just knowing the arrangement at any one site, we can very well predict the arrangement of other sites. In other words, there's a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. The examples of crystalline solids are sodium chloride, diamond, solid iodine, gold, quartz, etc.
Then polycrystalline solids. In polycrystal, it must consist of many small single crystals. Polycrystalline material have a high degree of order over many atomic or molecular dimensions. These ordered region or single crystal region vary in size and orientation with respect to one another. These regions are called as grains or domain and are separated from one another by grain boundaries. The atomic order can vary from one domain to another. The grains are usually 100 nanometer to 100 micro in diameter. Polycrystals with grains that are less than 10 nanometer in diameter are called nanocrystalline. Then amorphous solids. Just watch the video.
Now, let us discuss about amorphous solids. The arrangement of particles in amorphous solids is not in an orderly fashion. Sometimes in amorphous solids, we can find few tiny orderly arranged portions in between non-orderly structures. Since they are very small in number, they cannot influence the overall structure. Due to this, the overall arrangement of the particles in the amorphous solids is distorted. The examples for amorphous solids are glass, rubber, and plastics, etc. Now, if we notice carefully the glass windows of very old historical buildings, we will observe that these glass panes are thicker at the bottom as compared to the top of the window. This is because as the time progressed, some of the molecules on the top of the glass flowed down due to gravity and accumulated in the bottom, making it thicker. Please note that this process is very slow and takes hundreds of years. Due to this ability of amorphous solids to flow like liquids, amorphous solids are also called as supercooled liquids or pseudo-solids.
The branch of science that deals with the geometric description of crystal and their internal arrangement is called as crystallography. The symmetry of a crystal can be a profound influence on its properties. The atomic arrangement in a crystal is called crystal structure. The main aim of crystallography is to study the crystal structure. The structure should be classified into different types according to the symmetries they possess. In a perfect crystal, there is a regular arrangement of atoms. This periodicity in the arrangement generally varies in different directions. Now, space lattice. Just watch the video.
crystal lattices and unit cells. Consider a crystal. We know that the main characteristic of crystalline solids is its regular and repeating pattern of constituent particles. Now, when we replace these particles with representative points, a crystal lattice is obtained. Crystal lattice is defined as the three-dimensional arrangement of constituent particles represented diametrically such that each particle is depicted as a point. Such an arrangement is known as crystal lattice. There are 14 possible three-dimensional lattices known to us. These lattices are named after the French mathematician who first discovered it. Thus, they are known as Bravais lattices.
So, a space lattice is defined as a regular distribution of points in space in which every point has identical surrounding as any other point in the array. If all the atoms at the lattice points are identical, the lattice is called a Bravais lattice. There are such 14 possible lattices called Bravais lattices. Thus, the three-dimensional space lattice may be defined as a finite array of points in 3 dimensions in which every point has identical environment as any other point in the array. Arrays are arranged in exactly in a periodic manner. Then lattice points.
Now we know what is crystal lattice. Let us study some of its characteristics. First one, each point in a crystal lattice is called lattice point or lattice site. Second one, each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Now, if we observe this crystal lattice, we can notice that there
in a perfect crystal, there is a regular arrangement of atoms. It is very convenient to imagine points in space about which these atoms are located. Such points in space are called lattice points, and the totality of such points form the crystal lattice or space lattice. Let us now consider the case of a two-dimensional array of points, as shown in figure. Here in the figure, we can consider this as lattice points. So it represents a space lattice, but it is in 2 dimensions. So we can represent this lattice in terms of these parameters. Look at in the figure here. The distance between two consecutive points in the y direction is termed as b, and the consecutive distance between x direction is termed as e. So a space lattice in 2D can be represented as T is equal to N1A plus N2B. The vectors A and B are known as the fundamental translational vectors, and N1, N2 is a pair of integers whose values depend on the lattice point. In 3 dimension, the space lattice can be represented as T is equal to N1A plus N2B plus N3C. Hence, it should be remembered that a crystal lattice refers to the geometry of set of points in space, whereas the structure of the crystal refers to the actual ordering of its constituent ions, atoms, and molecules in the space. Basis or pattern. For lattice to represent a crystal structure, we associate every lattice point with one or more atoms. That is, a unit assembly of atoms or molecules identical in composition called the basis or pattern. Just consider the figure. In the figure, there is, in every lattice point, there is 3 atoms or molecules. It repeats in both directions. Okay. So we can take it as this lattice we associate it with a basis or this pattern. When the basis is repeated with correct periodicity in all directions, it gives our actual crystal. The crystal structure is real, while the lattice is imaginary. By lattice, we only consider such positions only. Okay, then when there is some atoms or molecule in such positions, it gives the crystal. So look at the figure. Here, the basis or pattern consists of 4 molecules or atoms, and it is added with this lattice. Here the lattice means some position. Then this basis is repeated in the lattice, so we get the crystal structure. Basis plus lattice give the crystal structure. I repeat, by lattice we means some position for accumulating the molecules or ions or atoms. Then when the molecules or ions or atoms situating at the corresponding lattice points, we get the crystal structure. Don't confuse with lattice points with atoms. Lattice points are some infinitesimal points in space. Lattice point do not necessarily lie at the center of the atoms. It is only a position. The crystal structure is equal to crystal lattice plus basis. Okay. It is observed from the figure that the basis consists of 4 different atoms. It can also be observed that basis is identical in composition, arrangement, and orientation. In crystal like aluminum and sodium, the basis is a single atom. In sodium chloride and potassium chloride, etc., the basis is diatomic, whereas in crystal like calcium fluoride, the basis is triatomic. In our example, in the previous example, it is consists of 4 atoms.
Now, if we observe this crystal lattice, we can notice that there is a small group of lattice points that repeats itself again and again to form an entire crystal lattice. This small group of lattice points is known as unit cell. Therefore, unit cell is the smallest portion of a crystal lattice. When repeated in different directions, generates the entire lattice. A unit cell is represented by three edges A, B, and C represented along X, Y, and Z axis. Please note that all these edges may or may not be mutually perpendicular to each other. In some cases, they are mutually perpendicular to each other, and in some cases, they are inclined to one another. In this unit cell, the angle between the edges B and C is alpha. The angle between edges A and C is beta, and the angle between edges A and B is gamma. Overall, a unit cell is characterized by 6 parameters, that is A, B, C, which are edge lengths, and alpha, beta, and gamma, which are phase angles.
So unit cell is the smallest portion of a crystal lattice, which when repeated in different direction generate the entire lattice. Unit cell is the basic structural unit or building block of the crystal structure. Lattice is made up of a repetition of unit cell. A unit cell is characterized by 3 lattice vectors A, B, C and 3 interfacial angles alpha, beta, gamma between them, which are called as lattice parameters. This is unit cell in 2 dimension and unit cell in 3 dimension. The smallest component of the crystal, which when stacked together with pure translation repetition produces the whole crystal. The vectors ABC, that is the translational vectors ABC, may or may not be equal. Also, the interfacial angles alpha, beta and gamma may or may not be right angles. Based on this condition, there are 7 different crystal systems. Thus, in a cubic system, A equal to B equal to C and alpha is equal to beta is equal to gamma is equal to 90 degrees. If the atoms are existing only at the corners of unit cell, the 7 crystal system will yield 7 types of lattices. More space lattices can be constructed by placing atoms or particles at the body center of unit cell or at the centers of the faces. Bravais showed that the total number of different space lattice types, obeying the conditions that every point has identical surrounding, is only 14. Hence, they term as Bravais lattice. Then the difference between unit cells and primitive cells. Primitive cells may be defined as the geometrical shape which, when repeated indefinitely in 3 dimensions, will fill all space, and it is the equivalent of one lattice point. The unit cell that contains one lattice point only at the corner is known as primitive cell. The unit cell different from the primitive cell is that it is not restricted to being the equivalent to one lattice point. In some cases, the two coincide. That the lattice unit cell may be primitive cell, but all the primitive cells need not be unit cell. That is, unit cell may be primitive, but all primitive need not be unit cell. And the difference between primitive cell and non-primitive cells. Look at the figure. Here, in this unit cell, the atoms is positioning at the corners only. So it is a primitive unit cell. But here in the non-primitive unit cell, one atom or particle is at phase center, so it is non-primitive. There are two distinct types of unit cell, that is primitive and non-primitive. Primitive cell contain only one lattice point, which is made up of lattice point at each of the corners. Non-primitive unit cell contain additional lattice point either on face of the unit cell or within the unit cell. So, have more than one lattice point per unit cell. So, I stop here. Thank you.